Okay, so now the next thing that we have here in the context of basically the scientific method is called a scientific law. Scientific law, or basically it's also called a law. Basically they call it law as well. So basically a law or a scientific law is some sort of relationship between two or more physical quantities. So I can say that a relationship between two or more physical quantities, and that is true as a general rule. Basically, when I say as a general, of course I will explain all of these, what they mean or what I mean by them. So when I say a relationship between two or more physical quantities, so for example, a physical quantity is, for example, mass is a physical quantity. For example, time is a physical quantity. For example, length is a physical quantity. For example, I don't know, luminous intensity is a physical quantity. Or electric current is a physical quantity. And there are other physical, for example, pressure is a physical quantity, but then it is defined based on the base physical quantities. We have the base physical quantities, and then we have also the derived physical quantities. So for example, pressure is one of those derived physical quantities. We have, for example, pressure as well. Or we have the volume as well, right? Volume is basically length times length times length times length is equal to volume. That's based on length. Or you have basically, for example, speed. Speed is a derived physical quantity which is based on length and time. It's the ratio of length and time, and so on and so forth. So now if I find in a particular context, for example, suppose that in the context of gases, if I find some relationship between pressure and volume, then that relationship, if I express it in mathematical terms, that relationship is called a scientific law, or a law basically. And that, when you call something a scientific law or a law, what it has to be a general rule, meaning that, for example, in the context of gases that we just talked about, it has to basically apply to, for example, all kinds of gases. If in the case of, for example, all kinds of gases, for example, there is such a relationship between pressure and volume, then you can call that a scientific law or a law, meaning that it has to apply to a large, basically, array of cases, or to a large number of cases, basically. So so now talking about basically pressure and, for example, volume, we can talk about the same thing in the context of gases, for example. Now we have picked pressure and volume, we have picked pressure and volume in the context of gases, and what scientists have found over the years is that basically in the case of gases, the pressure and volume have an inverse relationship, meaning that they have basically observed that when in the case of a gas, when you keep the temperature constant, if of course you keep the temperature constant, when you increase the pressure, then the volume decreases, and when you increase the volume, then the pressure decreases. So that means that pressure and volume have some sort of inverse relationship if you keep the temperature constant, right? Now, and this has been true in the case of almost any kind of gas that we knew basically all around us, and so we could say with all certainty that this rule applies to all gases that we could find, right? And so for the same reason, they have called it a scientific law. Now, this scientific law, basically scientific laws usually are expressed in terms of mathematical terms. For example, if you say that if you denote pressure by P and if you denote volume by V, I can say, because I know that there is an inverse relationship between these two physical quantities, I can say that P is proportional to V, but if the relationship is direct, meaning that if when you increase the pressure, the volume also increases, that then the relationship is direct, and then I would write it this way: P is proportional to V. If the proportion is indirect or inverse proportion, then I would write it as P is proportional to the reciprocal of V, or 1 over V, right? And this one is actually the case for gases. So now you know that in mathematics, when this is basically proportionality sign, and we have also the equality sign. In order to turn proportionality to equality, you have to basically multiply one side of the equation by some factor. For example, if I say that, for example, 8 is proportional to 4, 8 is proportional, of course 8 is proportional to 4, but if I want to turn this into equal sign, I have to write my 8 over here and 4 over here, and then basically multiply one side of this equation by something, which happens to be a 2 over here. So if I write 4 is 4 times 2, then that is actually equal to 8. But then of course I can say that 8 is proportional to 4, right? So I can take this as a constant that had to be basically multiplied by 4 in order to get this 8. So I can do the same thing over here, meaning that if I basically do a large number of experiments and set some value for the pressure, and then, for example, measure the volume of the gas in many different cases, and keeping of course the temperature constant, what I will notice is that basically there is always this constant of proportionality that I have to multiply by one side of the equation, so that P and V basically, so that I can turn this proportionality sign into an equality sign, which means that then I could multiply a C by, for example, this side of the equation, and write this as, for example, P is equal to, for example, C divided by V, meaning that I have multiplied the C by the right hand side of the equation. And I can call this, for example, the proportionality constant. As I can call this the proportionality constant. So So now I have a relationship between pressure. I have a relationship between the pressure and volume and of all gases. Let's say of all gases for the sake of simplicity and for the sake of this discussion. And this relationship between the pressure and the volume of all gases is called a scientific law. It tells me that in any gas, in the case of any gas, when you increase the pressure, the volume is decreased, or if you increase the volume, the pressure is decreased. That's basically what it says, but then I have to write it in mathematical terms. And so what that means is that and so what that means is that then you can call it basically a scientific law. And now there is one important thing that we need to take into consideration in the case of this scientific law that we have found. And of course we know that this scientific law is true in the case of all gases, no matter what sort of gas you pick. But the point here is that basically the only thing that this scientific law tells you is that basically when you have a gas, any sort of gas, when you increase the pressure, the volume is decreased. When you increase the volume, the pressure is decreased, right? That's all that you know about that. That's all that you know based on this scientific law. More than that, you do not know. And what I mean by more than that is that, well, of course, you know this sort of relationship exists between the pressure and the volume, but why is it that this relationship exists between pressure and volume? Meaning that, what is the reason behind that, right? That we do not know. Based on the law, we do not know the reason. And the reason, of course, is important for many reasons, because for example, if all that you know is that this relationship exists between pressure and volume, then of course based on that you can for example report a couple of values, meaning that for example you can build some sort of measurement device that measures, for example, air pressure in the atmosphere, measures air pressure, and then based on that you can use a computer in order to compute the volume, for example, of air, which makes no sense, of course. And then you can put all of that data on a website, and everybody will be able to see that this is the pressure of the air at this moment in time, and this is the volume of the air, and nobody will be able to do anything with that. Or at the most, what you can do is that you can mix in a little bit more of science with that, the science of atmosphere and weather forecasting and that sort of thing. And then you can build, for example, a weather forecasting station or something like that. So there is not much that you can do with this scientific law, although it enables you to do a whole bunch of things with if you know basically this relationship. But other than that, there is not much that you can do. Meaning that, for example, if you know that, for example, if you know the reason behind this relationship, meaning that, for example, suppose that this relationship is there because, for example, gases at an atomic or subatomic level are such and such, and based on that, then this will be the relationship between the pressure and volume of gases, meaning that the relationship between the pressure and volume of gases is an expression of the structure of matter at an atomic or subatomic level. So then, if you have the tools, and if you know the reason, and if you know enough about this, if you know about matter at an atomic or subatomic level, you can go in there. You can go basically inside the matter. You can go inside. You can go as low as this atomic or subatomic level, and then make some changes there, so that you can cause something. So that you can, for example, so that you can, as an example, make some sort of gas that has these particular properties as far as pressure and volumes are concerned, and then that particular kind of gas, you can use it in some specific type of technology in order to build a gadget or achieve something or do something with that, right? So meaning that if you now know all of this, now you will be able to actually build some sort of specific gas that has some sort of specific properties when it comes to pressure and volume, and then that sort of specific gas will be able to, and using that you will be able to do many different types of things. You can build many different types of measurement equipment, space exploration, and so on and so forth, right? But as long as you do not know the reason, of course, you can use gases exactly in the way that they behave, and then you will not be able to change the behavior. That's the problem with this, right? So now for the exact same reason, what people have done down the ages is that they, for example, they have noticed this sort of behavior in gases, for example. They have basically noticed this kind of behavior in gases, and so based on that, they have actually understood this relationship, this scientific law between the pressure and the volume of gases. But then scientists have constantly asked themselves, why is this relationship at all true? Why is it that basically gases have this sort of behavior when it comes to pressure and volume? And so that sort of endeavor takes us to basically theories and hypotheses. So now basically in order to find out what the reason is, you have to build a theoretical model. You have to build a theoretical model. So what this theoretical model does for you is it's just a mental logical framework that you build using thought. And of course you can use all the possible things that we already know about science, when all the relevant facts that we already know about science, and then we can put all of those, basically all of that logic and all of that science and all of those thoughts together, and then the result of that becomes a theoretical model. The theoretical model, what it does for you is that it enables you to think about things, meaning that without some sort of structure of mind, of course, you will not be able to think about anything. You have to have some sort of structure of mind, and you have to think based on some rules. Otherwise, your thoughts would be all over the place in the air, and they would achieve absolutely nothing. So this theoretical model, actually what it does is that it gives you some basically structure for your thoughts, and then based on that you can think in order to find out what is the reason behind the behavior of gases when it comes to pressure and volume, for example. So now again, going back to the scientific laws, we said that the scientific law, all that it tells you is that there is this relationship between the pressure and the volume of gases. It doesn't tell you why that behavior is there. The only thing that it tells you is that that sort of behavior is there. More than that, it doesn't tell you anything else. So then basically now I have to go through my notes. I usually don't write any notes. Okay, so we talked about the theoretical model, and this is page number 10. And so basically, as I mentioned, the theoretical model is a logical framework made of analogies, other relevant scientific facts that we already know, some, for example, mental images and models and things like that. Some sort of explanation and logic and all of that are put together, and that helps you to basically think and explain the behavior of gases when it comes to pressure and volume. Now in this basically mental framework that you have built, which is called the theoretical model, of course you have to explain things, and when you don't know anything about the subject, of course your explanations are most of the time not valid, right? Because they're based on nothing. You're thinking about something you know nothing about, so you have to basically improvise, put together some explanation that seems logical to you, and then worry about the validity of that explanation later when you will do some sort of experiment, so that you can verify whether your explanation was actually right or not, right? So now these explanations that you put together, which are most of the time, well, not true, they are basically called hypotheses. These are called hypotheses. This is also an important word or term, hypothesis. These are called, and the plural for that, as you know, is hypotheses. So these are called hypotheses. These hypotheses are simple tentative explanations that you use in order to basically add to your theoretical model, so that your theoretical model seems to be complete, seems to be able to basically explain whatever it is that you're trying to explain, right? So now basically we understand what the theoretical model is. We understand that basically hypotheses are part of that theoretical model. And now let's say that you come across, for example, some scientific law, for example, the gases and the pressure and volume. and you investigate and you build a theoretical model. Now you have your scientific law, you have done some investigation, and you have built a theoretical model. And you think that basically your theoretical model is absolutely correct, at least it seems to be correct logically, and so of course your model is I mean, you cannot say that your theoretical model is absolutely right unless you basically do some experiments in order to test your theoretical model. What I mean by that is that, for example, you build a theoretical model about the behavior of gases when it comes to pressure and volume. And then in your theoretical model, you explain that because of this and because of that and because of this and because of that fact, this is the case, right? So the reasons that you use over there, that tentative explanations that you use over there, of course, they have to be correct. Otherwise, the theoretical model has some problems. Now, whatever you say has some sort of implications or consequences. For example, in your reasoning, you say that, for example, because the structure of the atom is such and such, then that is the logical conclusion and that is the logical implication of that. And as a result of that, basically the behavior of gases are so and so and so. Now, in my reasoning, what I have said is that because the structure of the atom is such, that is the case. Now I have to know whether the structure of the atom is actually so or not, right? So now I have to devise an experiment in order to test whether the structure of the atom is actually so or not. And so that becomes one experiment. And then I have used another reason somewhere else, saying that because of this, that is the case. And then I have to go and devise another experiment to test that line of reasoning. I have another line of reasoning somewhere else. I have to go test on that. I have to go and test that. And so as a result, you have to do a whole bunch of experiments to test each and every part of your theoretical model. And whatever sort of implication or prediction that your theoretical model has, you have to verify that through experimentation. Now, if the model's predictions turn out to be wrong based on the experiments that you perform, then what happens is that you have to make changes or modifications to your theoretical model, or sometimes you even have to abandon the whole theoretical model, because sometimes it's just so wrong that you cannot mend it anymore. You have to throw it out and build a new theoretical model, right? Now, on the other hand, if your theoretical model survives repeated testing, meaning that you test all the possible cases that come to mind, and it survives that repeated testing and all the different types of tests that you need to perform, that achieves your theoretical model achieves the status of a theory. Achieves the status of a theory. And so you can say that basically a theory is basically a tested explanation of the behavior of nature. Is a completely tested explanation of the behavior of nature. It is an explanation. It's not a law. A law tells you this relationship is there. The theory tells you why that relationship is there. It is the explanation for the scientific law, right? So now there is one problem here. And that is basically we said that you had to do all kinds of experimentation so that you can make sure that basically every part of your theoretical model is absolutely correct. Now the problem here is that it's absolutely not possible, I mean logically not possible, to do every possible experiment to prove that a theoretical model is wrong. You cannot, I repeat this sentence, you cannot do every possible experiment to prove that the theoretical model is wrong, right? So what you do is that you do a number of experiments that come to mind, and then based on that, after a while, if your theoretical model stands the test, basically is successful in repeated testing, then you call it a theory. But that does not mean that you have actually proved that your theoretical model is absolutely not wrong or absolutely correct. It could be that you haven't done a certain type of experiment, and if you had done that sort of experiment, that your theoretical model would have been proved wrong, right? And you haven't done that experiment, so you just simply don't know. But meaning that you cannot ever actually be 100% sure that a theoretical model and therefore the theory is 100% right or correct. But that's not a problem, because as long as the theoretical model is working for you without any problems, so you have no problems and you have no complaints, and so we have no problem, we are good to go. As soon as, for example, some other scientist in some other part of the world does some sort of experiment, and the results of of his or her experiment prove that, for example, your theoretical model is in some respect, for example, wrong, then of course you can come back to your theoretical model or to your theory, make some changes, and correct yourself. And sometimes you even have to, even suppose that, for example, you develop a theoretical model, it achieves the status of a theory, and it works for humans for like 100 years. And after 100 years, some other scientist does some sort of experiment that proves that theoretical model that we developed 100 years ago was actually not correct. Even after 100 years, we sometimes have to abandon the whole theory completely altogether, and then basically find a new theoretical model and therefore a new theory in order to basically explain the same natural phenomenon. So that is basically the whole story behind the scientific method. So to recap here, so we were talking about the scientific method, and different parts or the different elements of the scientific method that we discussed were observations. These are the key points that you need to understand in the scientific method. Observations, conclusions. Then there is basically scientific laws. Then there is the scientific laws. Then there is basically a theoretical model. Then there is a theoretical model. Then there is hypothesis. Then there is hypothesis, and then there is theory. Now, if you understand this much about if you understand the meaning of all of these terms, observation and conclusion, scientific laws, theoretical models, hypotheses, and a theory, if you understand these terms, that means that you have understood the scientific method. Otherwise, you need to go back and watch the previous video and watch this video as well. If I have failed to basically explain this not properly, please let me know. Or, I mean, if you have any particular questions, please let me know. I will try to answer those questions. So I hope that this video was helpful to you, and I'll see you in chapter 2 of the book. Thank you.